Okay, two disks are mounted together on the same axis and can be brought together so that they couple and rotate as one unit. The first disk, 10 kilogram mass, 1 meter radius. The second disk, spinning counterclockwise and 200 revolution per minute. The second disk, with mass of 20 kilogram and 2 meter radius, spinning clockwise and 100 revolution per minute. We want to find the angular speed of coupling. Okay. Just like that, you have two disks. One is 2 meter arm. The mass is, what's the mass for the first? 10 kilogram. Okay. R1, 2 meter.
Should be 1 meter.
1 meter or 2 meter? 1 meter, okay. And M1 equals to 10 kilogram. And you have another disk, R2 equals to 2 meter. M2 equals to 20 kilogram. Okay? And the first one is counterclockwise. So counterclockwise. Okay? The rotational velocity is, what's that? 200. And this one is clockwise. Omega equals to 100. Okay? And then you bring them together. They will couple to form one object. And then you are going to have some object like this. Okay? Okay, they will rotate to some direction together. Okay, we don't know what direction, let's say, in this direction. And we want to find the angular momentum, not angular momentum, the rotational velocity, angular speed, omega, for this, the final state. Okay, this one, the equation you're going to use is the angular momentum conservation. Okay. You can compare this with some collision. If you have one object with some momentum, another object with some momentum, and if they collide and stick together, so the initial momentum 1 plus the initial momentum 2 together should give you the final momentum, right? The collision. And here, this one has some angular momentum. This one has some angular momentum. After the coupling, okay, then the summation of the two angular momentum should give you the final angular momentum. And the reason here why the angular momentum is conserved because it doesn't have any external torque. The coupling force is some internal force. Okay. Without external torque, the angular momentum should be conserved. So basically what we are going to do is to calculate because P naught should equal to P final. And the P naught should be P1 plus P2. Okay, P naught 1 plus P2 and equals to P final, right? We have two objects.
Can you move the wheel?
Hmm?
Can you move the wheel?
Okay. So, and then we need to calculate the not P, sorry. This is not the linear momentum. Okay, we should use angular momentum L. So we need to calculate the three angular momentum. The angular for this one, and this one. We have many different expressions for the angular momentum. And here, which one should be used for this stuff. Okay, like we have M, V, R perpendicular, or we have I omega. Which one should be used here? I omega. Because we are trying to find angular speed omega, right? That's one reason. Another, physically, they are extended body. Remember, I omega is for extended body. M, R, V, those equations are more for one particle in rotation. Okay. So that means we need to calculate the three. Okay, you can see here. Let's call this is omega 1, this is omega 2, this is L1, this is L2, that's a final L. So here, if it has a total, so we need the rotational inertia I1, rotational inertia I2, and this total rotational inertia. And so the equation then will be I1 omega 1 plus I2 omega 2 equals to I omega, right? Okay, by the way, here I shouldn't put the plus side here. We need to make sure we have the correct side. So for the positive and negative side of this given angular momentum, this one should be positive and negative.
Positive.
Positive. How about this one?
Negative.
Negative. So it should be positive, negative. Okay. Any question? That's the equation we're going to use to calculate omega if we know all other terms. Now let's look at how can we calculate. First, omega 1 and omega 2 are given, but they are not in the standard unit. So you have to do the unit conversion. So in the standard unit, what is omega 1? You remember how to convert this unit. Okay, our object should be make it to radian per second. Okay. How can we do the unit conversion? So I'm going to do it this way. You have 200, the number. Now, the revolution has to be converted to the radius. What is the conversion factor between the revolution and the radius?
2 pi.
2 pi. Each revolution equals to 2 pi radius, right? And then 1 minute should be converted to 60 seconds. Okay, so it will give you this, and you are going to get some number. Okay, I can keep the pi at this point. So 40 pi over 6, so it's 20 pi over 3 radius per second. Is it correct? Yes. Okay. Pi is of course 3.14, so you can get a number finally. And then this one, omega 2, should be, if you do the calculation, it will be 100 2 pi radius divided by 60 seconds. So it will be 10 pi over 3 radius per second. Okay, so that's omega 2. Any question here? Okay, that's the first thing you pay attention to. The unit conversion from the revolution per minute to radian per second. Okay. And then we need to figure out, so now we have this, we need to figure out I1, I2, and I. I1, okay, is the rotational inertia. That's a disc shape. So what is the rotational inertia I1? The center is the axis, of course, goes through the center, so it's the center of mass rotational inertia. 1/2 m1 r1 squared. That's the rotational inertia for a disk. You have all the number 1/2 multiplied by 10 multiplied by 1 squared, so it's 5. and I2 will be 1/2 M2 R2 squared equals to 1/2 multiplied by 20 multiplied by 2 squared. Okay. So it equals to 4. Okay. How about I, the total angular momentum after the coupling? How can you calculate it? It's not a regular shape. You cannot use any definition equation, but it should be this, right? Angular momentum, if you have several different parts, the angular momentum is simply the angular momentum for each individual part. Okay, you can add it, so it's 45. And then you put all these numbers together, you can calculate the final angular momentum, right? Final speed. Okay, any question here? So, okay. Here, we want to use the angular momentum conservation. Several issues need to pay attention to. Unit conversion, the sign for each term, and how can you calculate the rotational inertia? Question?
Does the direction not matter before you add the ion?
Okay, angular momentum, when you add them, please note angular momentum is something like the mass. They can only be positive. So there is no positive negative side problem. The only thing you need to pay attention to, of course, all of them, you need to talk about the rotation, not angular momentum, rotational inertia. Rotational inertia about one same axis. Okay, but all of them should be positive. There is no negative I, because they're kind of the mass, the rotation. Okay? So that's why total mass is simply equals to m1 plus m2, just like this. Any other question?